NGSolve. So when I was preparing this, I was thinking about who would be here. Of course, some people from basic introduction, how to work with MPI and NGSolve. So when I was preparing this, I was thinking about who would be here. Of course, some people from our group who are very well versed in NGSolve, but who maybe don't have a lot of experience with MPI. But that's something that doesn't only hold for our people. I think also you wouldn't come to the seminar if you didn't already do some stuff with NGSolve. So I thought, okay, I will take some knowledge over the MPI, or sorry, over the Python interface and NGSolve for granted. And in exchange, I will start at 0 for MPI, because there's probably 1 or 2 people here who only have, who may have heard of MPI, but maybe don't really know what this basically is. So in the start, I will very quickly talk about what MPI is and when and why we need it. And even if for the user, you usually don't need to concern yourself with the low-level technical knowledge, but I think it's still important and nice to know kind of how we got into this situation. So I don't know, maybe your code doesn't run as well as you think it should. Maybe it runs slower than it does in a smaller computation. And probably it's easier for you to figure out why if you kind of know what's happening in the background. And then the main chunk is going to be a basic explanation of how the different components of NGSolve work with MPI. So first of all, how do you even get something started with MPI, and how do you compile NGSolve with MPI? Then, of course, the main building blocks, so meshes, spaces, and linear algebra objects. How does the use of MPI change our use of these building blocks? And all of that stuff up to that point is very generic. This is stuff you have to deal with in any application you are trying to parallelize. What is more specific to every problem and what has to be tailored more towards the problem are iterative solvers, preconditioners, and that kind of stuff. So I want to stay a bit light on that side. And instead of showing you a lot of very specific examples, I'm trying to give you an overview of what's possible easily and where you can start looking if your problem is a bit goes over the scope of what you can do very easily, where you can look for further support and how you can maybe take it to the next level. And the last part in this middle section is going to be a short introduction or some short suggestions how you can handle visualization. Unfortunately, that's a bit complicated with MPI, but there are 2 solutions which are maybe not as convenient as you may be used to, but which are absolutely doable. And lastly, depending on how many questions there are, how fast I am, I would, if we have time, I would really like to show you a little bit about the PETSc interface I have been working on for the last, or within the last year or so, because I think that really opens, with very limited amount of work you have to put in, it really opens up a lot of new functionality you can use with MPI. So what is MPI? Why do we need it and when do we need it? The answer to the last question, when do we need it, is very simple. We need it when we are trying to make our code work on supercomputers. Unlike machines you have at home, or probably most of you have at your institutes, which are small servers which are basically built like this. So you have a bunch of processors that sit on shared RAM memory, and these processors can just access this memory very quickly and very efficiently. But on supercomputers, you basically take a bunch of those machines, you put them next to each other, and you lay a communication network between them in order to allow them to work together. And you might say, okay, I really don't care about how the hardware changes. I just want some software solution that obfuscates this additional layer of communication that is needed in order to get data that is stored here to here. But the problem is that this communication network has a higher latency large and is much slow and a lower throughput than your typical shared memory access by a large factor. So what I did here is I did completely randomized memory reads, one after another, as fast as possible on one of our, on the vector. This is one of the machines we have at the Institute. And I was looking, okay, how many megabytes or gigabytes per second can I load from well, the different levels of the cache, RAM and DRAM. So this stands for distant RAM. And this is just the part of the memory that is the farthest away from the physical processor you're running on. And you see that the latency goes from a couple of cycles to 100 cycles, or order of 100 cycles. And we always get hundreds or even hundreds of megabytes at least, or even gigabytes of throughput. In contrast, I did the same thing, but instead of reading directly from memory, I read something from memory and then I send it through this communication network to another core. And I looked at, okay, what is the latency now and what is the throughput now? And we see that the latency is much, much higher. It's thousands of cycles. We're in the, we're leaving the nanosecond scale. So even like there are approaches that try to completely obfuscate this distribution of memory to different machines from you. For example, I think this is called PETSc. This is not, if you use that naively, this is not going to give you very performant code. So this is really a difference in memory latency, which we have to consider in our programming approach in order to get a performant code. And the MPI library, or an MPI library, is something that allows you to do that. Basically, it's a C library that gives you a bunch of functions that allow independent but related processes to explicitly communicate with one another. And these libraries contain a couple of hundred C++ functions, which the most iconic of those are MPI send and MPI receive. So when you want to send data from one process to another, on the sending process, you explicitly have to call this MPI send function, and on the other process, explicitly the MPI receive function. And these MPI calls always get stuff like a data pointer, where to read from or write to, the size and type of data to be exchanged, destination and source of messages that are exchanged, as well as usually a tag, which is something you can use in your application to differentiate between different communications, and also an MPI communicator, which is basically a universe in which processes can communicate. So this is quite low level. And I want to stop with this low level here because as an NGSolve user, you probably won't really interact with this directly. Instead, you will interact with parallel NGSolve objects that are distributed between the nodes and that use this MPI library in the background. But I think it's important, again, to know what is happening in the background. So in the background, these smart C++ objects use this very low-level MPI library to communicate between the different processes. So how do we get an finite element code to run with MPI? How do we get it to run in a supercomputer? The approach is very generic and basically taken by every MPI parallel finite element software out there. You take your mesh and you partition it into different submeshes, and then you assign one of these submeshes to each processor. Every processor just stores one chunk of the global mesh. And with help of the MPI library, you somehow have to always make sure that these submeshes stick together properly, and you do the right stuff for any operation that concerns a subdomain boundary. So let's start at the very basics. How do you start a job with MPI? So first, in order to make NGSolve use MPI, you need to have an MPI library installed and turn on use MPI in CMake. So this should, in most cases, be everything you need to do. But when you are actually trying to set this up on a supercomputers are always unique systems. There is sometimes, most of the time, often, there are some additional problems, but this is the important stuff. If you just want to try this out at home, really, this should be everything you need to do. And then you start an MPI computation with this command here. So you call MPI run minus npn. This says, okay, dear MPI library, start n processes, and all of them should execute this entire command. So with this, we would start n independent processes, all of them start Python, and all of them execute this file.py. And in order to avoid confusion, I want to mention one more thing. With MPI configurations of NGSolve, we also install this NGSPy script. This is basically the same as Python 3. It just preloads some libraries, because sometimes with a combination of MPI, especially old OpenMPI libraries and MKL libraries, we have linking issues. And this NGSPy just preloads all of the needed libraries and then starts Python 3. So I just wanted to get this out of the way so you don't get confused later on when I use it. And one final hurdle is that the NetGen GUI does not work with MPI. So the NetGen GUI works with an MPI configuration, but only if you just start netgen file and not MPI run minus np10 netgen. So this is just because MPI and visualization is sometimes kind of difficult. For visualization, what I will be using is two things I will also show you how to do. On the one hand, which is probably the most important case, is how to use ParaView and VTK files. And the other thing for smaller computations, if you just want to do a sanity check on a solution or something like that, there's also a way to recycle the sequential GUI by saving solutions and later looking at them sequentially. But for the purposes of this talk, I will also be using the this, maybe you have already heard of it, this new alternative NGSolve GUI, which Christopher Lackner and Matthias Hochsteger are developing, which is completely written in Python. And I also have a hacked version of an old version of this new GUI, which works with MPI, but is very unstable. So I did this for myself. So I had something for debugging, but I think it also makes a very nice tool to show you some things. But this is really nothing you can use in your workflow because it's, as I said, not very stable. So let's get started. And the most basic building block we need to concern ourselves with is what is called an MPI communicator. I mentioned it before very shortly. An MPI communicator is a kind of universe which all the procs you start with MPI run are part of. And within a communicator, these can communicate with one another. And they have a unique number. So they are numbered 0, 1, 2, 3, 4, and so on. Whenever you start an MPI communication, the communicator which contains all of these processes is called MPI convert, or just MPI word. And from this, you can create subcommunicators, which are only shared between a couple of processes. But this is really kind of advanced stuff, and we will not need to use this much of the time. So let's start Python 3 in this case. Oh. Okay. So we load NGSolve, and then we just print out this global MPI word variable is this MPI convert. This is the handle to the communicator which all ranks are part of. Then we print out the rank and the size. So we have ranks 0, 1, 2, 3, 4, 0 to 4, so a total of 5 ranks. Now, okay, so what I did now, I started 3 Python instances which run this script and they communicate together, and I piped all of them to a different output. So let's see what this MPI world has to offer. You can do a barrier. So if we execute a barrier here in this rank 2 or 3, absolutely nothing happens, because the barrier is a synchronization point. This will only return once all 3 of these processes have entered the barrier. And just for convenience, we also give you this max, min, and sum of the communicator. So you can sum up integers. But this is really just for convenience. If you want to do something where you really want to directly interact with this MPI stuff more than these convenience functions, there is a specific Python extension to directly access these MPI functions. But for the most part, this is all you have to use this is all you need to use to directly from MPI. Sorry, it's a bit, this is going to take some getting used to, doing all of these talks from home. So this is the basic universe we communicate in. And next is the basic building blocks. The first building block you need to start a finite element computation, that is a mesh. So how we already saw what the basic approach would be with meshes. It's a parallel mesh is supposed to consist of a local submesh plus some information on how these submeshes stick together. And there are some remarks here. Firstly, every single proc will get one part of a parallel mesh, except rank 0. The reason for that is that in ancient times, rank 0 used to do the visualization, so it didn't do any of the computation in order to offset that. Nowadays, the visualization doesn't really work with MPI anymore, but still, for historical reasons, rank 0 still gets no part of the mesh for now. In contrast to the mesh, which is very memory heavy, the geometry is usually just a very small object, so it doesn't really cost us anything to have the entire geometry information present on all procs. And lastly, the mesh generation is not MPI parallel, so we will have to generate on one proc and then distribute it to all the other ones. While we have to change how we generate meshes, loading meshes from file works just as usual. And lastly, one important point which we will see right now is that we are really only working with local submeshes, and the enumeration of vertices, elements, edges, and so forth is completely local. There is no explicit global enumeration. There is just an implicit one that is defined by how the meshes interconnect. So if I go back here and so let's see what happens. If we start 3 ranks and we try to just as usually generate a mesh from a unit square and draw it. And here I'm using 3 instances of this new NGSolve GUI, or I should be, if it works. There we go. Okay, so I have rank 1, rank 2, and rank 0. And then I have, okay, I have the same window 3 times. Why is that happening? The reason is that, well, now we literally told literally told every rank to generate a mesh from this geometry. Every single rank. So every rank just generates a mesh and then converts it into an NGSolve mesh. So this is not what we want to do. And we see if we access the communicator associated to this generated mesh, every single rank is rank 0 of 1 in this mesh communicator. So that literally gave us the same mesh 3 times. So let's see how we actually do it. So if we are rank 0, we generate the netgen mesh and then we distribute it to this communicator, to this MPI world. And if we are not rank 0, we receive the mesh from this communicator. And then we convert it into an NGSolve mesh. And here we can see one rank has this half, one rank has this half, and this is rank 0 who has absolutely nothing.
What is zufällig, dass das genannt? Sorry, was it by purpose that the mesh was split in the diagonal, or?
It's not on purpose, but it is to be expected. So the library we use to partition the mesh is called matrices, and matrices tries to find a partition such that each part is as equal in size as possible, while also minimizing the surface area or the area of the interfaces. Because later on, when you define when you do linear algebra with spaces defined on the submeshes, the amount of data you have to communicate over MPI is related to how many geometric entities and how many degrees of freedom procs share. So matrix tries to minimize the surface area of tries to minimize this communication volume by finding a minimum interface. So in this case, it looks very pretty, and generally you will not expect to be the interface to be something like this, so you expect it to be a smooth line in some sense.
Okay, thanks.
Okay. So one important thing to note is that here, this really only distributes the mesh. The geometry does not need to be distributed. It has to be set explicitly. So let's look at what we have here. We have one circle. Inside the circle, there is another circle. We generate the mesh, we distribute it, and then we curve it. So let's try this out. First sequentially. Okay, yeah, we can see the exactly circle, bigger circle, and a nice curved mesh. And so, okay, something went wrong. Okay, we did distribute the mesh this time, but we have no curvature at all, although we curved the mesh here. And the reason is that if we do it like this, we just have to explicitly set the geometry. And then we again get what we want here. So, and what I mentioned earlier, yes, okay. So this is now this hacked version. I don't know if you can see this very well. Okay. so we can see here is point number 0, 1, 2, and 3, and so forth. So the points in this left half, which is assigned to rank 1, are numbered from 0 to 19. And if we go to the number 2, it's the same. There's 0, 1, 2, 3. Okay, I can't find 2, but here's 2. So the points and elements are really numbered locally. We have no idea how the rank 2 has no idea how the mesh looks on this side beyond this interface. But the points along this interface are numbered consistently. So we know this is an edge which I share with process 1. My local enumeration here is 10 and 15. And the local enumeration on the other side will not be the same, but it will match if we restrict it to this entire interface here. And this is how we find out how the submeshes stick together. So
excuse me, Lukas.
Yes?
So how do you make the numbering to be consistent on the interface?
In the beginning, you have the mesh on rank 0, and then you chop it apart and send it out to the other processes. And while you chop it up, you have to take care that the enumeration stays consistent.
Okay, thank you.
Okay. I'm sorry, I hope you can see these pop-ups I have coming up here. Okay. So essentially, when we distribute this mesh, we lose the global mesh, and instead we gain a bunch of local meshes plus information how they stick together. The next building block the next step is to define a finite element space on this distributed mesh. And again, as we will continue to have the case throughout the section, is the parallel object is the local object concerned with the local mesh, plus some object that sticks the local objects together. And for finite element spaces, this object that keeps track of how the spaces stick together are called the parallel DOFs, because they take care of the parallel degrees of freedom. So when in Python you write down like hcurl of mesh, you literally write down, I define an hcurl on my part of the global mesh. Plus, I want to have an object that tells me how the degrees of freedom are shared with neighboring domains. So we have like a domain, which is a local mesh. We have a space on this local mesh plus some interconnectivity information. This means that essentially every local mesh with local subspace is one big finite element. Because that's what a finite element is. It's a domain. It's a space on this domain, like a bunch of triangles. And for an H1 space, just polynomials restricted to these triangles, plus information how the degrees of freedom stick together. For H1, they have to stick together in such a way that the function always continues. So let's take a look. So this is the same as before. We define this same geometry, we distribute it, curve it, set the geometry, and then we do the exact same thing as oh no, sorry. Okay, there we go. What happened? Is someone sharing their screen? I can't see anything anymore. Oh no.
Yeah, me too. I had the same problem last time in the lecture.
Yes, I cannot see anything too. Only some shadows.
I think it may be because Zoom popped up something. Can you move your screen to another screen and then see if behind your window there is some Zoom stuff? I think I had that before as well.
For me, it normally works. Joachim, can you try to share your screen for a moment? Then Lukas can do it again. For me, that worked the last time if I switch the sharing. Because you are the host, I think you can share. Yes. So this is Joachim. Lukas, geht's bitte wieder?
Yes, just I have to try to get everything lined up.
Jetzt kannst du wieder sharen.
Okay. There was some pop-up in the background and okay. Okay. Just get this here and
Okay. Now we are again back.
sorry, I have no idea. Sometimes this happens and I still have not figured out how to fix it.
It's okay. Now everything is okay.
Okay. So this is the same you would do without MPI. You define an H1 space on this mesh. And here we give out the number of degrees of freedom in this space and something called end of global. So for example, rank 4 has 16 degrees of freedom and 39 global degrees of freedom. This literally means the end of is the degrees of freedom in my local mesh, while globally we have 39. And then we take a short look at this parallel DOFs object, which when you are working with MPI from Python, you will probably not to have interact with too much, but I want to still explain somehow what kind of data structure this is. So this basically can tell you three things. Firstly, it can tell you which procs are exchange procs. So of all the procs in our computation, which are the ones I have a common boundary with. So in this case, the rank 4 has ranks 1, 2, and 3 as exchange procs. Rank 0 is not included because rank 0 has no DOFs because it doesn't have a mesh. And then it can tell you for every one of these procs, it can tell you which degrees of freedom are shared with it. And for every degree of freedom, it can tell you which procs it is shared with. So let's maybe, let's do it like this. Okay. Let's maybe turn this one on and okay, so this is rank 1. Rank 1 is this chunk of the mesh. Sorry, this is all a bit finicky. Okay. And we have an order, and we have an order 1 H1 space. So we have 1 degree of freedom per vertex in this mesh. This is rank 2 down here. And here we say DOFs shared with rank 2. Oh, sorry, this is rank 3. DOFs shared with rank 3 are 2, 7, and 10. So these are the vertices numbers 2, 7, and 10. But if we go here and we grab rank 3, it will tell you, okay, I share with rank 1 DOFs 4, 8, and 11. This is 4, 8, and 11. So this is essentially how all of the parallelicity is stored. You just have local enumeration of degrees of freedom, of row numbers, of elements and edges. And then you have somewhere a table with these ones I share with those procs, and the transpose table with rank 3, I share those 3 DOFs. And we only ever have local enumerations, which are kept consistent. Okay. And this means that degrees of freedom are in fact shared between different procs. So this degrees of freedom would be shared between those three. And their supports are partitioned into the different submeshes. So this is this parallel DOFs object. It can give you the information which, so DOF to proc and proc to DOF mapping. And down here, I did a lot of hacking to get this nice graphic here. Okay. Okay. Oh, and that also broke. Great. Good. Next step is to define linear forms and to know how do we store vectors, and therefore how do we store vectors in parallel. Again, a parallel object is a local object plus parallel DOFs. Yes, these are vectors that belong to grid functions or right-hand sides. So they still need to know the information of how DOFs are connected, plus something new, which we call a parallel status. And the reason for this is that there are actually two ways to define this local vector here, which makes sense, which are related to the different kinds of vectors we're usually dealing with. So firstly, we have vectors that are coefficients of finite element functions. So the ith entry of a vector like this is the coefficient of this function for the ith base function. This is what we call it. And then it makes sense to say the local vector vi, so the vector stored on proc I, is just that what happens when we take the global vector and we take out the entries belonging to this local finite element space. So if we go back to the example before, this means that the full value of the global vector is stored by every proc that shares this DOF. The second kind of vector we are dealing with are dual space vectors. So for example, let's look at an entry of a vector that belongs to the right-hand side. So that is a functional applied to the ith basis function. So in this case, it's just an integral over the computational domain, a vector times this basis function. And this decouples into some overall elements that where the support is somehow part of, and the integral of f times phi only over this element. So this means the global entry is sum of some element contributions. And this is exactly the same for MPI. We saw before that subdomains with subspaces are basically nothing other than large elements which we glue together. And this is what we call a distributed vector. So in this case, the global vector is made up of these local vectors by summing them up with embedding matrices. So this embedding operator here takes a small vector for one subspace and gives you a large vector for the global matrix. Again, we see we never actually store these global vectors. We only ever store the local vectors plus information in which status the vector currently is. So let's look at an example. Maybe if then this should be clear very. This should be clear relatively quickly. Okay, this, as I said, it's not terribly stable and sometimes oh my God, there we go. That sometimes happens. I have no idea why. So what do we do here? So we define a linear form on a space defined on a parallel mesh. And we proceed as normally. We add some contributions and we assemble the vector. And then we look, okay, so f.vec, what kind of object is this now? And we see that now it's a distributed, yes, so this is an assembled vector, it's a distributed vector. And a distributed vector, and any vector has a dot local vec, which is a local vector, which has the status not parallel. So this is really just the local vector without any kind of parallelicity information attached. If you want to manipulate values directly, you can either do it through this vector or this one, although this one is usually safer because here you have guaranteed that nothing you do will mess with the parallel status in any way. This is a direct handle to just the memory that is locally stored. On the other hand, if we do a grid function and we set it to something, we get a cumulated parallel vector. So this is a vector that belongs to a function, and this is a vector that belongs to a functional. This is cumulated and this is distributed. And what we can also do is we can trick this, so we can draw this. Well, it's just a constant one function, but we can also manipulate this GUI into doing something that is wrong. We can construct a grid function, we can set it to constant one, and then we call dot distribute on this vector. This means this vector is converted from a cumulated vector into a distributed one. And then we directly set this parallel status to cumulated. So now this is a vector which is in distributed status, but it thinks it's in accumulated status. And then we draw it with this hack together GUI. And we see what the distributed vector is. The accumulated vector has full values everywhere. And values where those two measures coincide, there is this guy stores a 1 and this guy also stores a 1 here. Whereas here, this guy stores 1 and this guy stores 0. And that is the difference between distributed and cumulated vectors. Now, in principle, all of the NGSolve objects should work correctly independent of what status vectors are which you plug in. But it's still very important to know the difference between those two in order to know how bilinear forms and matrices work. And when you do code for your own and you do complex solvers, you have to stitch together lots of linear algebra objects, lots of linear algebra based matrices, oftentimes in order to get the total solver. So you really have to know what is a parallel matrix. And again, we have a local matrix plus parallel DOFs, plus another set of parallel DOFs, plus an operation type. So this is not a typo. Really, every parallel matrix has two parallel DOFs because it has to know how are input vectors shared and how are output vectors shared. These can be the same, but they don't necessarily need to. And then there's another thing, which is the operation type. So if you look at the matrices as representations of operators, there are different classes of operators you have to deal with when you do finite elements. So there are C2C, or what we call C2C operations. So operations that take a cumulated vector and give you a cumulated vector back. So these are operations that take finite element functions and give you out other finite element functions. Examples would be embeddings or interpolations from one space into another. Or if you are working with static condensation, the harmonic extension would be an example of this, because it takes the solution for the wire basket DOFs or for the wire basket and interface DOFs, and it gives you back the complete solution. It gives you the solution restricted to only the wire basket DOFs, and it extends it into the element interiors. The second very common operator are cumulate to distributed operators. These are matrices you get out of bilinear forms, because these take vectors, so trial functions, and they give you functionals. And then there are two more types which are more rarely seen. There's the distribute to distribute operation. So this takes one right-hand side and gives you another right-hand side. An example would again be this time the transposed harmonic extension, because this takes the right-hand side and it manipulates such that you get the right-hand side for the Schur complement system. And then one which you actually you probably won't ever use directly is distribute to cumulate. So this would take a right-hand side and give you a finite element function. For example, an inverse matrix or preconditioners would be of this type, but usually these operations are all special classes that don't fit into this simple scheme. So let's look at some examples. So same here. Now let's first look at a cumulate to distribute operation. This. Okay. So we assemble it by linear form and look at, okay, what do we get out? Okay, we get a parallel matrix out. Okay. And as with the vectors, we can also access the local mat, which is now of the type sparse matrix. So this is a parallel matrix wrapped around a space matrix. And this A matrix has the type cumulate to distribute. It has row and call part-offs. So this is how a row vector, so an input vector is shared. And this gives you how an output vector is shared. And a second very simple example, or a second example for a cumulate to cumulate operation, which is the other one you will probably deal with often. So we take this vector h1 and we take an h curl, and then we use this convert operator, which I've been working on recently. So this gives you an operator that takes a function in V and gives you a function in W. If V is a subspace of W, it's an embedding. Otherwise, it's an interpolation. The specifics here don't matter very much, and it's not yet in the master because I have some issues with compatibility with certain compiler versions. But this can be either an embedding or an interpolation. And we see the type of the, oh, sorry. You also have to say, yes. So we see this, in this case, it's an embedding operator, is a cumulate to cumulate operation. So this means that matrices, what we basically store are these diagonal contributions to global matrices and an operator type. And what we have to do is we have to transform the input vector into either a cumulated or a distributed vector. We have to apply the local matrix, and then we have to set the output vector to the proper parallel status. So maybe let's try to actually get a problem solved until the end of this talk. So for simple cases and smaller problems, we want to use direct solvers, and also for debugging purposes and such. And with MPI, there are basically two options you have in NGSolve. There is, on the one hand, the master inverse, which is basically just a disguised local inverse, because what this does is it sends all of the local matrices to the master proc to rank 0, and then does a local inverse on rank 0. The second option is MUMS. So this is an external dependency you have to build with NGSolve with use MUMS. It stands for multi-frontal massively parallel sparse direct solver. It's developed, I think, at INRIA in France. And this is an actual MPI parallel direct solver. So this can get you to a couple of 100,000 degrees of unknowns. But these are still all direct inverses, so these don't really scale to millions of unknowns. But, you know, let's maybe actually get something solved. Yeah, so nothing much to see here. We do this the exact same way. We take the a.mat, which is now a parallel matrix. We give it 3 dovs, and we say we want to invert it with mumps. And that solves our problem. Now, visualizing this is, as I touched on very shortly, a bit more difficult. And there are basically 2 options. You can either serialize solutions. This means that you gather all of the local vectors of the global solution, and then NGSolve sorts them together in the right way and writes it to a file. And then you can afterwards load this coefficient vector into a serial computation and look at it with the NetGen GUI. So let's see how this looks. So we define our mesh, our space, and if we are running this script in MPI parallel, we set up the problem and we solve it with mumps. And then we call grid function.save with parallel equals true. So this parallel equals true is the switch to say, don't just write the grid function data into the file, but actually write one big vector on the master block and gather together all of the local ones. So let's run this. So, okay, this gfu.data is completely unreadable. It's just a binary file. And now we can run the same script again without MPI. And in that case, oh no. We load this data into the grid function and then we draw it. And again, here we have to give it the switch parallel equals true so it knows how the output is formatted correctly. So if you want to do a sanity check, this is something you can do for smaller problems. Of course, if you have a huge computation, then you won't really be able to draw this locally at all. But it's still nice to have as a fallback. But really the main way you probably want to visualize solutions of really big computations is with a VTK output in ParaView. ParaView is a visualization program which is really great for what it does. It's not very convenient to use. It's not very tightly coupled to NGSolve, but it is extremely scalable. And if you compile it in the right way, it also supports a server client model where you can run the server, which also renders the images on the cluster with MPI, and you locally only run a client, and you get this picture which takes a huge amount of computing power to render from a cluster and display it locally. But that goes a bit above the scope here. I just want to show a very simple application. So we again solve with mumps, the same as before. Then we construct the VTK output. By the way, I think this code was written by Christoph Lehrenfeld, if I'm not wrong. So he's also in the audience. So thank you very much. That has saved me so much work. This is extremely useful. So you give it a file name and what you want to save, and then you call do, and it's and we give a different file name on every rank. So every rank writes one of these VTK files, and then we can start ParaView. Yeah, on. Hold on. Okay, so then we can load all of this in here. And I really want to show you only very quickly how this looks. So we load all of these separate files. Okay, there we go. We load them in here and then we can look at it. But really using ParaView is correctly is a science unto itself. It's hugely, but it's also scriptable with MPI. You can also use it to make videos and stuff like that. But I really just wanted to show you that that's probably the option you want to use. Because as you have already seen, that the MPI parallel GUI we have is, it's held together by a spit basically, and it's not for, and it's also not scalable. So VTK is really the way to go. Now, everything I have, or almost all I have shown until now has been very generic. This is stuff you need in every application you want to use NGSolve for. What is always problem dependent are iterative solvers and preconditioners. So you have to know if you really want to get into MPI a lot, this is probably where you will have to spend a lot of time, or a good chunk of your time, unless you have a problem where a solution already exists. Because preconditioners are always problem specific. And in this place, in this spot, I really just want to tell you what works with MPI, which is built into NGSolve, and how to start on getting more stuff on, and where there are starting points, how to use different extension packages to maybe also tackle other problems. So built into NGSolve itself, the iterative solvers, the Krylov-based solvers all work. So there's nothing specific you have to do to make this work with MPI. The preconditioners that do work with MPI are Jacobi and block Jacobi if you only have blocks that that don't cross MPI boundaries. Maybe probably the poster child is the BDDC preconditioner. This will get you to for medium problems, you will get really, really far with this. Really only once the coarse grid problem becomes too large for this to solve directly. This has been used for a long time. This has been in NGSolve for a long time, and this is probably what you will use in the start. And there is also an interface to the HyPre library where we can use the scalar AMG or algebraic multigrid they have, as well as the Maxwell AMG they have. Then there is a small package I am developing, which is called NGS AMG, which contains algebraic multigrid for H1 and elasticity problems. And here you also can do multiplicative Gauss-Seidel and block Gauss-Seidel, again with the same restriction of blocks crossing domain boundaries instead of only additive here. So you can install this as an extension. And the one thing I want to give a very short overview, because I'm running kind of late, is the PETSc interface, because I think really this is probably interesting for a lot of you. So PETSc stands for Portable Extensible Toolkit for Scientific Computation. And it's basically a C library which contains a huge amount of features. So basically anything you would ever need for scientific computing is in here. It has all of the usual iterative solvers, so GMRes, CG, MinRes, all of that stuff. It has in itself implemented a lot of preconditioners like AMG, and it has a lot of interfaces to other packages such as HyPre and incomplete LU and stuff like that. Beyond these linear solvers, they also have implemented many different nonlinear solvers, so Newton, trust region, there are even some constraint minimization properties. And then there are two big extensions to this library. One is Tau for optimization problems, which I know basically nothing about. And the other one, which we are currently very interested in, is LabC, which has eigen problem solvers. So these solvers and preconditioners are green here because many of them are very easy to configure and usable basically from the command line. And all of that is included in our interface. Also the linear, the KSP, the Krylov space problem, and the nonlinear solvers are also basically all working. As I said, the Tau library have not looked at it all. For LabC, I have started on an interface, but it doesn't properly work yet. But I hope to get that running soon. And I think this will be also very nice. And this PETSc interface we have should not be confused with the Python, with the PETSc Python interface. So the PETSc Python interface is developed by the PETSc developers, and they basically just export their functions in their C library, which are quite low level, to Python. And our approach with this PETSc interface is to enable you to convert NGSolve objects to analogs which use PETSc in the background. So you can work on this on a very high level, and you don't need to get into the specifics of how PETSc works. So because I'm really short on time, let's just look at a very simple example. So here again, we do the same geometry and mesh, and we set up the same problem and the grid function. And here we start using the PETSc interface. So we import this NGSPETSc library, which you can find on GitHub. Then we take our A matrix, as well as information on the Friedhofs, and we convert this into a PETSc matrix. Now this PMAT is something that PETSc can work with, and also it's still derived from base matrix, so you can also incorporate that into all of the operator algebra we have on NGSolve side. And then we can set up one of these Krylov space problems. So it's a Krylov space problems with this matrix as the system matrix. We can give it a name. And then if there are any PETSc users among you, you will probably recognize this. So PETSc is built on a huge option database, which are basically strings as keys and values. And these allow you to configure at runtime what PETSc does in the background. And you have a lot of control. For example, here, the options for this specific object, we set it, okay, the KSP type, so the Krylov space problem type is conjugate gradients. We can set, for example, a tolerance, so it will iterate until the tolerance has been reduced by a factor of 10 to the power of 8. We can set the type of precondition it should use. And this tells it, okay, please print in every iteration the current error to the shell. And this is a KSP object, which can be used just like a base matrix. So the solution is the KSP times the right-hand side. And there we go. So, and nonlinear solvers work very, very similar. So I was not able to show you as much of this as I was originally planning to do. But I think if you want to do something where there's not already an option built into NGSolve from the start, there's a good chance you can find some way to do it over this PETSc interface.